Hello class. Today I wanted to, before we got started with our lesson, take a look at problem number 5 from last night's assignment, which had us integrating x sine y within these bounds. There is a neat property that allows us to create a product of two single integrals from a double integral. And you can do this as long as you can separate your integrand into an integrand in terms of x and an integrand in terms of y. So that's one thing that must be true. You have to be able to factor these. And in this case, it's easily separated. You have your x right here, and then your sine y right here. So it's easy to separate it into an x function times a y function. This won't always be possible. For example, if this was sine xy, that can't be separated because the x and y are contained in the sine function. However, in this case, we can easily separate those into two functions. A function g of x is x, and then h of y would be sine y. The other requirement is that the bounds are rectangular. So in other words, these bounds here are going to be numeric quantities and not functions. So 0 to pi halves and 0 to 2, those are both numeric bounds, and if we were to graph that area, it would be a rectangle. So what that allows us to do is take two single integrals instead of doing a double integral. So this, number 5 from last night, can be separated into the integral of 0 to 2 sine, x dx times the integral from 0 to pi halves of sine y dy. So all I have to do is the one integral in terms of x, and then evaluate it at the bounds from 0 to 2, and then the other integral sine y, and evaluate that from 0 to pi halves, and then multiply the results of those integrals together. And I just think it's a lot easier than carrying the double integral. So this is possible sometimes. And again, the requirements are that you can write this function, separate out and factor out the x versus the y, and also that you have numeric bounds. So that's just a little tip moving forward. Today, we're going to talk about how double integrals help you to find volumes. So the integral of a surface is going to give you the volume under that surface as it is achieved in R, which is our area on the XY plane. So above the XY plane to the surface. So you have your XY plane, and you will gather area from the region in the XY plane all the way to the surface. And so that's what taking the double integral does for you. And that is what we're going to practice today. So this particular problem asks to find the volume of the solid in the first octant bounded by the cylinder z equals 16 minus x squared and the plane y equals 5. So the first thing I'm going to do is just get a sense of what this looks like. So I'm first going to graph the cylinder in the xz plane because the equation just comes up in the xz variable system. And so looking at this, I know that this is an upside down parabola moved 16 units up. So the z-intercept is 16, and the two x-intercepts are going to be plus or minus 4. And because I'm only in the first octant, I'm actually going to erase the part of this parabola that is in the wrong octant. So I'm going to erase the negative parts of it because it's just not valid because that is no longer the first octant. So let me get rid of that. So this is the shape that I'm looking at, and I'm looking at that shape from y equals 0, which is on the xz plane, all the way to y equals 5. So you're going to imagine this being gathered parallel to the yz plane, kind of out of the screen 5 units. And so it looks like this, where one edge is this cylinder, but then oh, that was a fail. Let me try that again. I just have to redo that back edge. Yeah, that looks a lot better. Let me actually erase that. Yeah, there we go. And so we have this graph repeated over and over again until the plane y equals 5. So this is in y equals 0, and then we're just going to have it come out at us till y equals 5. So this here to here is 5 units. And if we consider the shadow on the xy plane now, we know that our x varies from 0 to 4. So our x varies from 0 to 4 because that's how much it's going to vary here. And then that's how much it's going to vary on the xy plane, 1, 2, 3, 4. And because it's in the first octant, it's bounded by y equals 0 and y equals 5. So that goes 1, 2, 3, 4, 5. And then it's going to be a rectangle in the xy plane. And that's that bottom of the shape that we're finding the volume of. So that is our goal, is to find the volume of this shape that is bounded by z equals 16 minus x squared. And then it's in the first octant. So you have this kind of squareness to it at the bottom and then at the back as well. I'm going to dare to draw this line down here and hopefully it still looks okay. So that's going to be achieved with our double integral. So I'm taking the double integral of the surface, 16 minus x squared, under the region, and you can do dx dy in any order. And so our x's will range from 0 to 4, because here we have 0 to 4 on the x-axis, and on the y's we range from 0 to 5. So that is our integral, which is going to achieve the volume of that solid. Since we just learned that little trick, I'm going to use it right now. So I'm going to say this is the integral from 0 to 5 dy times the integral of 0 to 4 of 16 minus x squared dx. And because of the trick we learned, the ability to separate these integrands into two separate single integrals instead of one big double integral, as long as we have rectangular coordinates and that it is separable. And because x and y there's not even a y in our integrand, so it's pretty easy to accomplish. So this is just going to be y from 0 to 5, which is 5. And this is going to be 16x minus x cubed over 3, evaluated from 0 to 4. So what we get is 64 minus 64 thirds. And then doing that math, we're going to get 128 thirds. And then that gets multiplied by our 5, which we got from the integral with respect to y. And then finally, I'm going to get a volume of 640 thirds. And that's our volume. So the tricky part about this is knowing what your bounds are going to be. So you have to think critically about where it's going to intersect the X and Y plane, if that's what you're integrating over. And just thinking about how telling you little details like the first octant helps you with your bounds as well. So I like to draw a lot of pictures, look at a lot of planes like the X, Y, Y, Z, and XZ plane through the process of doing this. Here is your assignment. Good luck.